Good morning, guys. So today we're going to talk a little bit about breakdown. Yesterday we did a real broad stroke kind of overview of the history of the theory of plate tectonics and how we got to that. But today we want to focus solely on and again, this is review from sixth grade, the evidence that Alfred Wegener had before he wrote his book, The Origin of Continents and Oceans, back in 1915. Um, so the three big things that Alfred Wegener had discovered was that he found similar fossils of plants and animals on continents that are now separated by thousands of miles of ocean. And again, when we talk about fossils, we're talking about organisms that existed millions of years ago, not hundreds of years ago, not thousands of years ago. It takes millions of years for organisms to become fossilized. He also found evidence that there were mountain ranges on opposite sides of the Atlantic Ocean, that the rocks of these mountain ranges were the same type of rocks, same kind of chemical composition, same kind of fossil life found in them. And so he found similar rocks in mountain ranges located on continents that, again, are separated by thousands of miles of ocean. And then he also found evidence that the climate of some areas was drastically different. And so we'll kind of talk about those three major things. Now, before we do that, I want to kind of briefly touch base with you about how we can date certain things. Now, there's two different types of dating. There's relative dating of things, and then there's like actual carbon dating of things that actually requires a process to determine exactly how old something is. But when we talk about relative dating, we're talking about if one thing is older than or younger than another. And so when we are looking inside the earth and we dig inside the earth and we find a fossil, and then we dig deeper and we find another fossil, because the second fossil is deeper or below the other fossil, we can say that fossil B, the second fossil, is older than fossil A. Okay. So just as an example, if you wear 5 different shirts during a week and you have your dirty clothes hamper in your room, and so when it's Monday, you wear your Monday shirt, and then when you get home, you put your Monday shirt in the hamper. And then you wear your Tuesday shirt and you put it on top of your Monday shirt. And as you go through the week, you can kind of go through here and stack the shirts like this. So in the hamper, this is how they would look, right? And so if you're looking for that red shirt, that Monday shirt, you know that you wore it on Monday, so it has to be underneath Tuesday, Wednesdays, Thursdays, and Friday's shirt, right? So anytime we stack something up, I mean, if you're stacking up cups, you put one cup down and then you put another cup inside of it. I mean, your first cup is the one at the bottom, right? So that's going to be the oldest cup, or the cup that was in that position the longest. So when we talk about how we date things or determine whether one thing is older than another, we can just look at the layers of the rock. And of course, the deeper something is, the older something is. So here's a couple of different diagrams that kind of show how we can look at the layers of the earth and determine whether something is older or younger than another organism when we find fossils. Okay. So again, the deeper we go, the older things are. All right. And we can look deep and we can go down here into this area right here and look up fossils of different plants and animals. And from those plants and animals, we can make some generalizations of what the climate was like. Okay. So if you find a fossil of a tropical plant down here, you can say that the climate during that time was tropical, warm, moist, wet, whatever you want to call it, lots of rain. And then up here, if you find in the same area above it, you find fossils of cactus or desert-like plants. You could say that, well, up here we found plants that grow in arid environments or dry environments. And then down deeper, we find fossils of plants that grow in tropical environments. And so you can make some generalizations and say, well, back in this time down here, then the climate must have been different than it is here, right? So as we dig deeper into the earth, we can make those generalizations. And so when we talk later on about the climate change evidence, that's the kind of evidence that Alfred Wegener discovered. Okay, so it's very important to understand that when we're looking in the earth for evidence of past life that used to live on the earth that may not live on the earth anymore, the deeper we go, the older that life is. Okay. Okay, so 750 years. So I did some calculations for you. 750 years on average it takes to make an inch of topsoil, right? So if it takes 750 years to make an inch of topsoil, and dinosaurs went extinct approximately 65 million years ago, we can calculate how many inches of soil has formed since the dinosaurs went extinct. And so all you got to do is a little bit of math. 65 million years divided by the average time it takes to develop an inch of topsoil. That's 86,000, should be 86,666 inches, 7,222 feet of topsoil, or 1.36 miles of topsoil since the extinction of dinosaurs. Now, that doesn't mean that we have to dig 1.3 miles deep, because of plate tectonics and the other changes that have occurred on Earth, erosion, weathering, and things like that. But that's just kind of showing you that soil is made from the remains of living creatures, so dead plants and animals. Their nutrients and their chemicals that make them up get absorbed into the soil when they die. Same thing with dead plants. When plants die, and little pieces of rocks get broken apart to form soil. So when we're digging, the deeper we dig, right, the older things are. So we would not expect to find a dinosaur fossil above a fossil or bones of a human, right? Because humans and dinosaurs didn't exist on Earth at the same time. And here's a little video here that you can watch inside the assignment in Schoology if you want, that shows you kind of a time lapse of how soil is created. And there's different materials in each one of these little containers that kind of show you how topsoil is created. Okay, so when things die, and they die in a natural way out in the middle of a field somewhere, eventually they are going to be buried by the development of more topsoil. And there's other things, like I said, about weathering and erosion can aid in the exposure of these fossils that were once buried very deep. Okay, so let's get to it. So let's talk first about the plant and animal fossils. So if we look at this diagram here, you can see, and I've color-coded the boxes over here on the left and the right outside of the map that show you where Wegener found evidence of these fossils. So if we just focus here, let's say on the red dots. So the red dots were an animal that looked like this, okay, land-going animal, not a sea-going creature at all. And he found fossils of this organism on this portion of Africa and this portion of Asia. Okay. Now, is it possible for that organism to have walked over here? Yes, because Africa and Saudi Arabia, which is right here, is actually connected to Asia, so you can literally walk that way. So that's just one piece of evidence that shows you that this organism was found in these two areas. This one here, another land-based creature, found fossil evidence of that creature on this coast of South America and the western coast of Africa, again suggesting that at one point in time these two continents were connected here. Same thing with the blue fossil, which is a Glossopteris, which is a type of a tree. They found evidence of this tree all over the place. They found it in South America, they found it in Africa, they found it in India, they found it in Australia, and they found it also in Antarctica. And we should know that trees like this don't grow on Antarctica, which suggests, and we'll talk a little bit more again later, that the climate of Antarctica was different. And if the climate was different, that usually suggests that the continent of Antarctica was located closer to the equator at some point in time in Earth's history. Okay, so again, evidence of the Glossopteris tree found all over the place. And we all know that Glossopteris trees can't swim, and their seeds are too heavy to be blown by wind that far. So again, that's evidence that suggests that all of these areas that we find the Glossopteris were once connected. And then the last example here is the pink organism here. Again, they found it here in southern South America and southern Africa, again, suggesting that these three dots here lined up with these three dots here, which is, again, evidence that South America and Africa used to be connected. So here I just want to kind of show you just an image of what scientists believe. Again, this is a theory of what Pangea looked like. And I like this map because it actually kind of shows you the actual continents, or names where the continents today were when all of the continents were connected. Okay, so you can see North America and South America, Africa here, Antarctica, Australia, India, and Eurasia, which would be a combination of both Europe and Asia. So this is what scientists believe Pangea looked like prior to the breakup. Okay. All right, so here's just another image that kind of shows you how they're all connected, and these are the same organisms that I showed you in the previous slide right here. So again, this kind of just shows you where these organisms were found and when all of the continents were connected together. All right, the next one of the pieces of evidence that we talked about was rocks and mountain ranges. And so scientists have gone out and looked and said that basically the rocks and the mountains, and this is the Appalachian Mountains here in the United States, are very similar in composition and structure to the rocks and mountains on this coast of Africa, which suggests that at one time these two areas were connected. Also up here in the Caledonian Mountains in Europe, the British Islands here, and then the eastern coast, of Greenland here. Again, suggesting that all of these pieces of land at one point in time were connected. So if we go back to the three things, we talked about the fossils and plants, similar rock and mountain ranges located on continents are now separated by thousands of miles of ocean. And then the last clue, again, is the climate change. So again, if we look here, we can see that these areas of when they were all connected, again, this is during the breakup. So this is like after Pangea, but before they were in the configuration that our continents are now. You can see how different areas used to exist near the equator. And we all know that climate is different. The closer to the equator we get, the warmer it gets, the wetter it gets. Our tropical rainforests are all located near the equator. You can see that Australia, India, Africa, South America all were very low towards the south and were probably covered in ice for a long period of time before they started to migrate to the north. And again, you see India here, which eventually slammed into southern Asia to create the Himalayan mountains. Okay, a couple other things I just wanted to touch base with you on. I kind of showed you an image on yesterday's notes about this. This shows you the age of rocks. And so this is the ocean floor. So we've kind of just grayed out all the continents and just looking at the age of rocks and the ocean floor. And what I want you to notice is the youngest rocks are going to be red, and then the oldest rocks are going to be blue. And so you'll notice right here, this is the Mid-Atlantic Ridge that we discovered back in the late 50s, early 60s as we were mapping the ocean floor. And we have dated these rocks, and we find that these rocks all exist between 0 and 9.7 million years old. But when we look at the edges of the coasts here and here, we find that these rocks are much, much older. Okay, 180 million years to the rocks here to the east coast of the United States and the west coast of northern Africa. We have these green rocks here on the coastlines of South America and Africa that are indicating that these rocks are somewhere between 120 and 180 million years old. So what that suggests is that new rock is being made along this edge, this ridge that's in the Atlantic Ocean. And it is this new rock that is pushing Africa to the east and pushing North America and South America to the west. So it's literally this crack in the Earth's crust that created or started the breakup of Pangea to today's current positions of the continents. And then when we talked yesterday a little bit about sonar, this is kind of a brief video showing you how sonar is used. Again, so we have boats that travel across the surface of the ocean, and they send down sound waves, and those sound waves will bounce down to the floor and bounce up. And using the simple formula that we learned before Christmas of speed is equal to distance divided by time, we can actually calculate the different depths of the ocean and see how the undulations and the mountains and everything exist underneath the water. Okay, and so from this data, then we can create these maps of the ocean floor to show you where the deepest parts of the ocean are, where the more shallow parts of the ocean are. And so it's that technology that we use to determine what the ocean floor looks like, because we can't, even though we can get in a submarine and go down that deep, we don't have windows available to us, so we can't really see what it looks like outside, and there's not a lot of light down there in the ocean. Okay, so again, from this, I've got a discussion board question in Schoology for today's assignment. Please make sure that you get it done. And again, let me know if you have any questions. Just send me a message. All right, guys, have a great day.